Okay. This is the last lab. uh, I'm going to, in today's lab, go through sort of the like fixed effects, briefly cover clustering standard errors, which we didn't cover in lecture yet. So I'll just show you how to code it, but you don't have to understand what it does. For the assignment for this week's problem set, you will be asked to describe what is happening to the regression result when you cluster standard errors. And you just have to describe. It just means you have to look for the things that are changing or not changing to sort of say, I think this is what's going on, right? And then Greg will explain in next week's lecture what standard errors or what's happening to the standard errors and why. And then I'm going to spend the part of the lab going through the data processing portion of your problem set so that if you were to follow along in lab, you would know how the variables were constructed. And I also give you the code to run all the analysis for the problem set. So in the end, the only thing you would have to do is work from a generated table that comes out of your code and read it and present it. And it's sort of the entirety of the problem set. It is harder to do than you might think because it's hard to figure out what all the relevant details are. But you guys have kind of had practice doing this. And whenever any kind of information was missing, I noted it in your problem set, so you should kind of know. But the idea is any table should be self-contained. So anyone who's just read the title of your paper, and maybe the abstract, or maybe not, can look at your table and your notes and understand it. Okay, anyways, so let me get started.
Can you tell us a little bit more about that group project you said earlier?
Yeah. So problem set 9 is where you'll be doing power analyses. Anytime you run a statistical analysis, you have to know whether you have enough of a sample size to detect some kind of effect or a prediction that's significant, right? So that null finding isn't just a result of a huge confidence interval in which no one can understand anything because you have a sample size of 10, right? And the idea is if you can kind of guess from the literature what the effect size should be and what the research design is going to be, then you should be able to figure out how big your sample size should be so you can figure out before you run the research how many study participants that you are going to have to recruit, which is important for budgeting because every data collection costs money. And you'll be doing a little bit of a cost-benefit analysis and the trade-offs between research designs or power. And that requires you to run 2 softwares. One of them is called Optimal Design. It's not as friendly. It works only on Windows. The creators of that program, I think they got so mad at people asking will you make this for Mac users? They've said, we believe there will never ever be a Mac version of this program. This is the first thing you see on their website, right? And then the other one, I think is called G-Power, which works both on Macs and Windows. But the problem set requires you to use both because G-Power, which works across platforms, doesn't allow you to do all this stuff that Optimal Design does. But it has a nicer interface. And we want you to get used to using both so that you can use the more the program with more functions when you need to, and then use G-Power when you don't need all of the functions, and a quick power analysis will work. And because it doesn't require data and the problem set gives you step-by-step instructions. I think this one was made by Greg, so I just made some slight copy edit. You should be able to do everything without any kind of help just by following the instructions and reading some bits and pieces of the user manual for the 2 programs. But because it's so detailed, you can very easily make mistakes. And I think it's one of those things that's nice to work on together. And you guys should get like identical answers. And so if you're gonna have to work together to like check every detail and make sure all of those details are correct, you might as well just submit one assignment. And so that's sort of the idea behind the next problem set. And that's why you won't have to spend time learning, like practicing anything in lab. It's just sort of an execution of things. And for any questions you might have because you get stuck somewhere, I'll be available for office hours like on Wednesday as per usual. Does that provide enough context for next week's problem set?
So this would technically be a group assignment and we can submit just one, and then how big would the groups be allowed to be?
It'll be this will be in the instructions, and I'll announce it, and Greg will probably announce it too. But in groups of 2 or 3, no more than 3. You can of course do it on your own, and that's totally fine. And like everyone should submit the same document, and just say like who your group members were. I'm gonna just randomly pick one person, download their file, grade it, and apply it to everybody in that group. So if someone submits the wrong document by mistake, that is, I don't know, that's up to you, it's up to you guys. And so that's how the next problem set will be handled. Cool. Okay, so let's get started with today's lab. All right. Let me move this.
Sorry, I was a little bit late. So this week's problem set will be like in groups?
No. Next week's problem set. Yeah.
Oh, okay.
This one you'll do like as you typically have done on your own, your answers in your own words.
Yeah.
And of course, if you need, you should not need any coding help. Every single code has been provided for you. The only thing you would have to change is like stuff like globals to make sure that your file paths are right. And the entire problem set is about presenting the results in a table and interpreting what's in that table.
Yeah, wouldn't make it easier necessarily, but yeah.
I just saves you some time. Anyways, so I'll get started. Unless there are more questions before.
Yeah, thank you.
Yeah, okay, cool. So you guys should have the lab files. This is for lab 9. And I don't know what happened, but it seems like some of the test score labels got lost along the way. So this block of code here you've seen before from a previous lab. I'm just rewriting it to label the test scores again. So that's all it is. I won't cover it. And we covered change models, residualized change models, instantaneous change models, accumulated effects, inputs models. For this lab and for the problem set, we'll just look at change models, simple change models, and residualized change models. And we've just given it fancy names, but for previous problem sets, you have already run these. You ran it, I think it was either in week 1 or week 2. And then you ran the residualized change sometime like in week 3 or 4. So none of the code is new, right? The way you interpret them is still the same. The way you talk about them is the same. We've just conceptualized it as simple change or residualized change. They just have fancy names now. There's nothing new. Okay. And so for the lab example, I went to the breakout room, PowerPoint, where you guys had examples of what kind of stuff could you like analyze with the Eccles K. Oftentimes people are looking at like test scores, predicting test scores as a function of self-control, or interpersonal skills as a function of internalizing, or externalizing as a function of SES and other family characteristics, or test scores as a function of sense of belonging, or a function of approaches to learning, or time on math. And we're just going to work on one of these, which is the first one, test scores and self-control. And I think the group has specifically called out reading test scores. So we'll just use those. Okay. And we'll first clean our main predictors for this example. We're going to look for everything that has the word control in it. And there's like parent reports and teacher reports. And I think we saw last time, like teacher reports of like child behavior and parents report of child behavior, they're very, very unrelated. So we have to pick one. But I just sort of see that like we have more measures of teachers like reporting on children. So we'll just use that one. But there are reasons to choose parents reports, right? If you find it to be more reliable, or if you're looking at something that's closer to home quality or something like that. Okay. And this is how I'll check these variables. It looks like they all start with T for the teacher reports and with control. So I just run a code book to sort of make sure that they look okay, and they don't. They have like these negative values. And I can make sure how many negative values there are by running this code, just tabulating across all of these variables. And looks like -9 is the only missing value, but we'll just make all of them missing if they're negative. And then while we're at it, for all of these control variables, we'll create a standardized version, right, with egen. So nothing new so far, just found our predictor variables, clean them, and standardize them. But if something's unclear here, let me know. If you're unsure about what's happening, just let me know. Now we're gonna look for the outcome stuff, which we know, just reading tests. But we want to use standardized reading tests. It just makes interpretation a little bit easier. We've labeled them. We've already worked with these. That's pretty easy. Our control variables, we have cleaned and made a bunch of control variables for previous labs and problem sets. We'll use the same one. We'll look at race, ethnicity, age, gender, birth weight, stuff in the house, mother characteristics, education, and then like overall SES in the house. Okay. We'll just give them nicer labels so that it just makes for a nicer table, or you have less editing to do. And then we're going to get ready for the analysis. You have to choose like which time periods do you want to examine, right? We have as early as time 1, and we have as late as time 6. That's kindergarten entry and 5th grade spring. But just in case the entry test is different from like a spring test, I'll just use time 2. I don't know if they are. So we could rerun the analysis, looking at how they do at time 1 and how they do at time 6 instead of time 2 and time 6. But this example is just bounded to time 2 and time 6. And if you forgot what these times were referring to, you could always just describe one of the reading test variables. Where we know 1 is kindergarten entry, 2 is kindergarten spring, and then 6 is 5th grade spring. And you can use like different time points too, depending on what your research question or interest is. Gonna make a quick sample indicator. And the way I'll do it is just making sure everything looks okay, nothing looks crazy. This negative is like a real value. These negatives are real values. I'll run an egen that says, tell me how many of these variables are missing. And then I want to make sure, because since we're using listwise deletion, meaning we're using records that have complete information, I'll just take the values for which we have 0 missing values, which is like 35% of our data. And this is just a way to double check that I've been coding this correctly. Everyone here, if they're missing any information, they're getting a 0. Only people missing no information are getting a 1, and that's our sample for the lab. Let's run 3 models. A level model, meaning like not using any kind of past information or predictor information, where this is where you predict an outcome at time 6 using whatever predictor variables that you have, not using what the outcome was at time 1 or 2 or an earlier time. That's meant by a level model. And then we'll run a simple change model, a residualized change model, and just to sort of get a sense for who's in our data set, right? We'll run a summary of all of our variables for the people who are in our sample, and then for everyone, right? Looks like people in our sample, they have higher than the average reading score, and probably a higher than an average measure of self-control. So they have more self-control than the other kids in the entire Eccles K sample. 10% Black, 14% Hispanic, 5% Asian, 5% other. This age doesn't make any sense because it was just taken at a particular time. Half are female, which is good because that's what you would want. Birth weights, I don't know what a small or big baby is, but some people will. 81 books on average in the house, 14% in which the mother was 30 years old or older when the baby was born, 20% born to teenage mothers. A little higher, above average SES. A fair amount of moms eligible for WIC benefits. Many who are high school, and I think this is some college, right? And 30%-ish with a college degree or higher. And you can compare it to these statistics too. This is like everybody in the Eccles K, where they get like a mean of 0 here, as you would expect, because these are all standardized. And so your sample that you're looking at here is sort of like, you sort of see a selection effect happening. They're not the typical sample, they're more of the higher performing sample. And maybe, right, there's a smaller proportion of them eligible for WIC, meaning they might be a more advantaged sample too. Okay. I asked Greg if we were going to go over missing data and how to control for it. And I think he wants to leave that for a different class. So I just want to give you the intuition that whenever you use list-wise deletion, like we have done for the entire quarter, you always have to worry about like who's in your sample. And for anyone who's interested in dealing with missing data, I can cover it in like a different like office hour for anyone who's interested, or I'll meet with you separately. Okay, so far all we've done is we've cleaned the predictive data. We have remembered what our control variables were. We have defined our outcomes, and now we're gonna run the analysis. And along the way, we'll store the estimates that we create from the models we run. And for every type of model, level model, simple change model, and residualized change model, we'll do one without controls and with controls. So as you see here, this is sort of a bivariate regression, regressing reading score at time 6, I think that's 5th grade, on self-control at the spring of kindergarten. And then the same thing repeated with controls. And for a simple change model, all you do is you generate a new variable where you take the difference between the 2 time periods. So Z read 6 minus Z read 2. This is sort of the reading gain between the two times. Again, just a bivariate regression with controls. Residualized change, as you've seen in class, it's just regressing Z read 6, the outcome at time 6, on your predictor of interest with the lagged time variable Z read 2. Again, without controls and with controls. Okay, and we'll just print these. And we won't print it in like an Excel, we'll just take a quick look. And this is what we have, right? You guys are used to seeing this, but these numbers are a little different. And it's hard to read across and make sense of them, right? Like, what would you think from having seen these 1, 2, 3, 4, 5, 6 numbers? What would you hypothesize about your understanding between self-control and reading skills? Anyone want to take a guess at making sense of these numbers?
I guess I can try.
Yeah.
So would these be the like slopes of our line in the sense that 1 unit increase of self-control would lead to a 0.214 increase in reading?
Yeah.
Okay.
That's how you would read this one, right? So Molly, what do you think is, like, as you look across, right? This is the level model. In case you want to look at the code, it's here. You add controls. This is the simple change model. Then you add controls. This is the residualized change. Then you add controls. What do you think? What do you think? What does this tell you?
Oh, well, I guess we would be able to see that the simple change is attributing too much importance to simple self-control, I guess, and that adding in our controls does take away some of the, especially in the models 3 and 4, because that one is very significant and then it becomes like totally insignificant or no
Yeah.
significance. So that means that the controls actually account for more of the change than the self-control measure itself, I think.
Yeah. Yeah. And you can kind of see a similar reduction from 1 to 2 and from 3 to 5, except they just somehow maintain are significant. This is like nearly halved, a little more than halved, right? And then a little less than halved, right? There's a big reduction as you add these controls. And as you know, means that the control variables might be explaining a lot of the outcome and not this predictor of interest. And so when you have, let's say you have the simple level model, and then now you look at the changed model, and let's say you were only looking at 1 through 4, what would you think about, like, how would you make sense of the relationship between self-control and later reading? Like this here suggests that there is a relationship, right? Kids with more self-control, they tend to score higher on reading in was it 5th grade? What about here?
I'd
guess-
say that self-control would be important, but wouldn't necessarily like result in growth. So maybe like the students with self-control will get like on average higher results, but that self-control wouldn't result in growth, something like that.
So yeah, I think I know what you mean, right? Kids with more self-control are gonna, for a lot of reasons, have better reading scores, but then they won't grow in grow in their reading skill because of self-control?
Yeah, something like that.
Something like that. Okay, I should first say, like, these are not easy to like make sense of. There's not a clearly one right answer. They could all be wrong also, like Greg showed, right? And so if you, yeah.
Can we say like over time, the effects of reading score would fade away?
So with this,
Or
the
they don't have
effects,
lasting effects or something like that.
so is the thing creating the effect self-control here? And are you saying that maybe from looking at these results, you could say that self-control in kindergarten has fading effects on reading skills? Is that your question?
Yeah, I think so.
So I'm not sure that you can say that, because in order for you to understand if something is fading, right, you would have to sort of look at outcomes at time 6, time 5, time 4, time 3, time 2, and then sort of see if sort of the relative like non-causal effects, right, are fading. I don't know that you can just look at the change in the level, right, with this gain score that you create to sort of say that there's fading. I think I don't think you can say that.
Right. Thank you.
Yeah. And I think the real complication comes when you're looking at models 5 and 6. Like, because this is still kind of showing some predictive nature between self-control and then later reading, although it is certainly smaller, just not as small as a simple change. And I guess you would read this as, you know, like in addition to controlling for these characteristics, you're also controlling for, you know, like old lagged outcome, meaning comparing kids with a similar reading score. And it's sort of awkward. Like Greg doesn't really like this. He thinks it's awkward and hard to think about for most people. But this is not significant, but this is. So how do you reconcile these two results from 3 and 4 and 5 and 6, or I guess just 4 and 6? But they're not answering the same question. So this is sort of where the change models, they give people lots of headaches, myself included. And this is where going from an empirical result to a conceptual understanding becomes much, much harder. And this is why Greg says, start with the conceptual model, then find this. And right now I keep using the words like predict or like correlates. You could sort of in the literature, and I've confirmed with Greg because this makes me feel a little bit uncomfortable, but let's say you have a proven causal model, right, between self-control and later reading in some pathway. Then you could sort of say, assuming this causal model is true, assuming this conceptual model is true, the causal effect of self-control in kindergarten on 5th grade reading score is this much. But you have to like caveat this with assuming that's true. So, and for a residualized change model, I'm not sure what that conceptual model is. except in the most simplistic sense of a lot of econometrics, where you just try and make the kids similar in everything that you can to isolate this effect. But it doesn't give you the same thing as just looking for, like, sort of changing the outcome to give you the change and the growth. And if the relationship between self-control and later reading doesn't look like the relationship between self-control and the growth in reading, maybe it's harder to sort of make the case, right? It's harder to make the case that there is a causal effect between early self-control skills in kindergarten and later, like, 5th grade reading score. This is sort of a more conservative estimate of the relationship between kindergarten self-control and reading in 5th grade. But I'm definitely not an expert in change models. And this is one of those things that you can bug Greg about, because he's done a lot of these change models. He's thought a lot about them. I haven't. Anyways, so going over this was sort of to give you also, like, a window into my confusion and uncertainty as I look at this. It's easier to think about this, but it's hard to compare these two things. I mean, you can think about doing this too, right? Like, as you interpret this, because you have done this before, where you just control for pretests. And you have done this before, where you have created an outcome where it's a gain score. When you compare across, it's hard to reconcile why they don't give you the same kind of answer, and one is more conservative than the other. Anyway, so okay, now for the problem set, you're only going to have to interpret this like simple change model. But I do ask you to, like, look across all of your models, sort of think about what concerns you might have, what hypotheses you might have, what additional analyses you might want to run to sort of, like, check what your instincts are saying. Like, if you look at these models and something feels uncomfortable, something feels wrong, or you can't quite make sense of it, you might have to start drawing out the conceptual model. And then you might have to test other hypotheses as to the extent that you can with the Eccles K. So that's all I'll say about this for now. And we can come back to this confusing, like, outcome, and then, like, mull it over further. But we might as well then add more analytical like tools to try and isolate the relationships between the predictor of interest and the outcome of interest. And as Greg has covered, I think twice now, we'll look at fixed effects. Okay, like, what Greg does in his study is he uses classroom fixed effects. And I don't know if you noticed, but he, in one of the slides, he says teacher fixed effects. And that's the same thing, kind of, not exactly, but more or less the same for the Eccles K. When you look for all the IDs, you have these teacher IDs. And if the kids have the same teacher, likely they're in the same classroom, right? Or maybe they're taught by the same teacher in 2 different classrooms. But I think the way the Eccles K was sampled, they didn't look at multiple classrooms for one teacher. I think they just looked at 1 classroom per teacher. So this is why you can use these variables on teacher IDs to get teacher fixed effects, which is equivalent to classroom fixed effects. Yeah. And let's build on the simplest model. This is regressing reading at reading 6 on control at 2, so kindergarten control. Right, this is a model we've seen before. And we want to add school fixed effects. And then we'll cluster the standard errors, which you don't have to worry about for now. But when you control for school fixed effects, right? So look for ID. These are our school IDs. We have school IDs for 1 through 7, right? We're looking at outcomes on 6 and predictor at 2. Which school ID should you use? Right? You have so many to choose from. likely you're going to choose between 2 and 6 and not another number. But which one? Right? And fixed effects is going to try and compare the students who are in that same school, right? Or at least school fixed effects are. Right? You're limiting the variation to the kids that go to that same school, but which one? I don't think we covered this, so but I just want to get your best guess at which one. Some stuff in the chat. Time of the outcome variable. Who does anyone else think it's the time of the outcome variable? And what would your reasoning be? Would it not be the predictor variable? So a couple of people think it should be the predictor variable. Can you share your instinct on why it's the predictor variable? Or if you want to argue the case for it should be the outcome variable, can you share your instincts for that? Whichever one. Guess, okay, fine. Why you guess whether it's predictor or outcome time?
I guess predictor because the predictor variable is what you think is predicting the outcome. So something that is affecting the predictor variable, you want to control for that, no? That's why I thought school 2. I mean, S2.
Can you say that in just a little bit more words? Can you like use more words to say what you said?
So basically you mean word. Wait, I'm not good at adding more words.
If someone said, can you elaborate? What would you say?
I would elaborate that, for example, what was it? I lost track of. So we're predicting reading outcomes in what's 6? Spring. I forgot, but we're looking at for example, if we're looking at reading outcomes in grade 3, this is hypothetical, I'm not following this data set, in grade 3, and we're predicting that reading outcome on like children's like problem behaviors in grade 1, then what our predictor variable is within children's behavior in grade 1. So whatever was happening in that classroom has an effect on the outcome.
I see.
That was a good elaboration. I would
Okay. Other people have guesses for why they believe that the predictor time is a better choice, or if you disagree and you believe the outcome time is a better choice, you can say that too. Like, just FYI, like the answer is given away here and here. And if anybody that has scrolled down, they'll see that the answer is the predictor, but you know, it's sort of an important exercise, right?
So I feel more compelled to speak now that I know my initial idea, right, even though I don't think my rationale is right. But anyways, I kind of have the same thinking as Fugo. So the way I think about fixed effect is like it's a control variable where you're holding something constant. So the reason I thought it was also the predictor is only because if I think about it as if it were some type of control, then that means you're holding the initial predictor constant because you don't control for your outcome because that's what you're trying to look at. You're trying to make sure you're holding whatever effects or relationships before you look at the outcome. If that doesn't sound like complete gibberish.
No. I mean, I think you guys are all kind of like collectively getting at different facets of the idea. So one way to think about it is school 2 is going to be much more exogenous than school 6, right? It's less likely that your entry into a particular kind of school, right, is affected by your predictor measurement, self-control at age 2 or at time 2, right? School 6 could sort of be a function of whatever follows your self-control at time 2. It can be affected by it, and just like you wouldn't exactly control for later outcomes, right, as a sort of like your mediator or whatever, you would sort of stick to the variation that's at your predictor time. Because what you want to do when you're adding in fixed effects is you want to limit the variation in this predictor variable of interest to the kids that went to the same school. So if you're going to limit the variation in time 2 control, right, to the kids that went to the same school, then you want to be cluster, like you want to use school 2, time 2 to limit that variation in that time 6. But also I think like in any and all change models, you will always want to use the one that's more exogenous, so that corresponds to predictor time than the outcome time. But it takes some time, like because you could find ways to argue for the other one, and maybe there is a way. I don't know when it makes sense to control like for fixed effects at the outcome time or the later time, but I'm not like super sure. Okay, so we're gonna clean the school variables. I mean, we can look at them, right? It's S2 ID. Let's do like list S2 ID, and we'll just look at the first 10. And that looks fine. It looks like a number, but then they have these zeros in front, right? We can describe S2 ID, and we know it's a string variable. And when you can't put a string variable into your regression, right? So you could destring them, right? So for, let's say for all of them, for 1 through 7, schools 1 through 7, right? Which is based off of S1 through 7 underscore ID. Let's just destring them, right? And generate a new variable, call it school 1, 2, 3, 4, 5, 6, 7. It's kind of nice. It can work, but it can be a bad move. This might be a bad idea. And we can like browse the IDs too. Where did it go? Right. Why is it a bad idea to just destring them? And you can browse the data to look for a reason. You can also look at this output and look for a reason.
There are these letters that are like in the IDs.
Yeah. So it didn't generate a school 7. Right? It said S6 ID and same for S7 ID. It contained non-numeric characters, so it didn't generate a variable. You can force them, right? If you hit force here, it will force it and it'll destring it, and any non-numeric characters are going to get a missing value. But you don't want to do that because then you lose data. And so what you can do is you can just create an entirely different one, right? So let's drop the ones that we have already created. So cap drop, school, whatever. We'll use egen, and one of the egen function is to use this thing called groups, and it'll just give, starting from the number 1, and arbitrarily assign every string value some number, right? So we'll do this and take a look.
So it would categorize them, right?
Yeah, it would categorize them. And so all of the ones that have 0, 0, 0, 1, they're going to get a 1. And then all of the ones have a 0, 0, 0, 2, they're going to get a 2. And the next one, which is 0, 0, 0, 0, 5, right? They're going to get a 3, right? Like these numbers are not supposed to line up. They're just saying, this is the first group. They're going to be group number 1. This is the second group. They're going to be group number 2. This is going to be the third group. They're going to be group number 3, right? Like agnostic to what these values are. They're just giving them a number to distinguish them into different groups. So this is a way to like clean string variables and make them numeric when their values don't matter and you only care about using them as sort of fixed effects, right? You don't care about a linear relationship between a group number or a school ID and an outcome. You only want to just control for each and every one of them. Okay, and now that we've like added a variable, right, called school, we might have to adjust our sample. You know how we created the sample here, right, using these variables alone. But now we've created a variable. Where is it? Yeah, now we've created a variable to control for school fixed effects, and we want to make sure they're not missing either, right? Because if they're missing, then they shouldn't be a part of our sample. And so I'm going to say replace, give them a 0, right? They're not going to get a 1 if it's missing school 2. That's the variable that we're going to use for school fixed effects. And then there's like one guy, there's like one person. So it's not like a huge deal, right? But you know, it keeps it cleaner. So every time you run sample lab9, right, as sort of your conditional, when you run your regression, like this one person will not be there. I mean, it's not going to be there anyways, but it'll be true for all of your models and not just your fixed effects models. So how you add these fixed effects, right? Greg has said, like, they're just a dummy variable in your equation. So if this is your regular equation, you can create a dummy variable for all of school 2, right? But it's a lot, right? You can say like tab school 2 gen and then like school 2 underscore, and it's gonna like create a dummy variable for all of those schools, right? This is school 1591, 1590, and then you can leave one out and put them in. But that's a lot, right? That's a lot to like write syntax wise. And this is why the I dot syntax is useful, right? Like since you don't want to do that, you can just say regress I dot whatever, your categorical variable. But even this isn't that great. Because if you think about it, there are lots of schools. And my data is still trying to print. This is a little excessive, right? This is you do not care about any of these numbers. You only care about this one, right? And so we're going to use different syntax. It's called areg instead of regress or reg. Same thing, except the school portion gets pushed to the option side, where after you have written out your regression like syntax, you say comma, absorb school 2. And this will be the same thing, right? And so let's copy this number, right? This is what we had before. We'll copy over the R score. Okay. Okay. And now we're going to run areg. Again, the only thing that's different is now instead of controlling it as a separate dummy in the equation, we just put this outside and absorb it. And now it tells you it had absorbed the variable school 2. These are your fixed effects. And your beta coefficient is 0.1689, 0.1689, standard error, 0.01145, 0.1145. T statistic is the same, your R square is the same.
Paul, do we
Yeah.
only use AREG because we need that option for absorb? Was that the only reason?
Yeah, yeah,
Okay.
yeah. There's another way to run this. You can say xt set. This is what Greg mentioned in class. This is like pretending that you have panel data. And then running xtreg, same equation, right? Like AREG, right? Outcome, predictor, if statement. And you just specify fixed effects. Because you can specify random effects or other effects, which you haven't learned. And it'll give you the same thing. Mostly the same thing. Your coefficient will be the same. Your standard errors will be slightly smaller. There are technical differences. It's because of the way that the computation happens in the background. I will cover those differences later for anyone who's interested. But it's giving you practically the same thing. Okay. And so we're now also gonna like go over the syntax for clustering standard errors. Again, you only have to just know how to run the syntax, right? So for using AREG to add fixed effects, the way you cluster standard error is you say cluster and standard error. And this will get explained in lecture. So just ignore it. It'll be there because you need it for the problem set. You should know what what's different when you add the cluster standard. That's one of the problem set questions. And everything here now is something you've seen before, the bivariate regression, unadjusted, meaning no controls, adding the controls, adding the fixed effects, right? School ID, adding clustering of the standard errors, which we won't cover, and doing it again for the simple change model, and doing it again for the residualized change model. And this will just print a table. And this time we'll actually print this. Okay, so you've seen this before, where I think the numbers, nothing should have changed. Where you saw that when you added controls to the simple change model, the predictor became no longer significant. When you added school fixed effects, the beta coefficient changes slightly, but not much more. And then when you look at this residualized change model, again, you see sort of a reduction from adding in control variables, but then it doesn't change very much when you add school fixed effects. So that's a question, right? Like you added school fixed effects, and likely my expectation was, and maybe this was your expectation too, that this was going to change, but it didn't, right? Like I just added in like 1,500 variables, right? And this did not change. What does this suggest? What does that mean? So I'll leave it to you guys to think about it. Greg in one of the lectures, Greg goes over like fixed effects, and he's like, "We now control for fixed effects, and then this happened. What does that mean?" And it's something I'll come back to. But if anyone has thoughts now, let's hear it. If not, we can take a 5-minute break.
Yeah. So can this mean that this like relationship is independent from like classroom?
What does that mean? Like use more words.
Means that their intercept was really like close to each other to begin with. Then adding fixed effects didn't change it that much.
Yeah, So move away from technical language and tell me what that means. If you think that the intercepts, like changing the intercepts or letting them have different intercepts didn't matter so much, what does that mean in terms of the way you think about it substantively?
I have no idea.
Yeah, it's hard to get used to. But you know what fixed effects were doing? What was fixed effects doing when you control for school fixed effects?
Greg said that it isolates the variance to within groups, so within the schools.
Yeah, so that means I'm now being compared to my peers in the school and not other kids in other schools. And so oftentimes when you control for fixed effects, these things change a lot, but it didn't. So what does that mean in terms of the variation?
Yeah, that's what I meant, that it is like independent. So probably every like classroom is the same. Like they have the same distribution and like there aren't much different.
Yeah. So one way to think about it, right? It's like using different words now from what Amin was getting at, is that even after you have limited the variation to within school, your coefficients and even your standard errors did not change very much. That probably means even before you control for school fixed effects, right? The key variation, most of it was probably within school. And so this is why even though you have constrained it to be within school, it doesn't change much because it was already most of it within school, is one way to interpret what's happening here. If a lot of the variation was between school, right? That this was sort of biased in the sense that, or let's look at this or whatever it is, that it was reflecting between school differences, right? Kids ended up in different schools because they had different self-control. Then limiting that variation to within school is going to reduce, right, the relationship between self-control and later outcomes. But this would suggest, right, adding in school fixed effects and the coefficients not changing very much, that most of that variation is really happening within school, or that's sort of explanatory of later outcomes, not school sorting. Right? You might have a hypothesis that the higher self-control kids are sorting into better schools, lower self-control kids are sorting into lower, like not as good academic schools, right? And maybe that's sort of explaining this relationship, but that hypothesis wouldn't hold given how little the coefficients change. Okay, so we'll take a 5-minute break. And when we come back, I mean, all labs are optional, but this is even more so. I just go over like how I created the predictors for the problem set, how I created the outcomes for the problem set, the control variables, we have already done this, so that you just have a better understanding of what's in the problem set. But like nothing, of course, like you don't have to listen to any of this, you can just read it too. So we'll take a break. When we come back, I'll go over the data processing for the problem set, and then I'll cover other questions and then puzzle over this table for anyone who's interested.
You can pause the recording maybe.
Okay. I think it's been like 5 minutes-ish. Oh wait, like a minute or so. Okay. Let's get started. If you're feeling sort of puzzled by the results, right? Like it's hard to think about them. It's like completely natural. Like I have a hard time comparing across change models too. They're just not as clean. I mean, I think they buy you a lot of credibility in your analysis, but I don't work with them often. I'm like working with an accumulated change model or an accumulated inputs model, but never easy. Okay.
Well, is it too late to ask you to review how to interpret the change models again? I don't, or maybe I'll ask you at a different time.
Let's all right, I should put this on the same side. Let's work on the problem set data processing, which shouldn't take too long, and then I'll come back and we can talk more about interpreting. And then if there are more confusions, then we can talk more about it during office hour. This is one of my crazy days where like starts at 8 a.m. nonstop till like 9 p.m. So I probably can't like stay much longer. But I can definitely answer more questions over email or talk about it during the office hour. Yeah, I'll try to keep the chat open. Sometimes it lets me look at it. Okay. So for the problem set, trouble finding words today, we're going to be looking at the relationship between academic achievement and then time spent on academic work. Right? The idea being, spend a lot of time on academic stuff, probably do better, right? Well, okay. So we're gonna search the data for like things that tell me about like time and like or how often. And of course, it's faster for me because I've already like looked for them. But you can see like how often reading, how often math, time for reading, time for math. That there are these variables, like, and you can do this too, right? That tell you like, oh, we have time for math at time 4 and time 2. We also have like, look for how often you do math. Well, what the hell does that mean? Like how often you do math. We can tab it. You're like, all right, tells you in terms of like frequency, like weekly, daily, less than a week, couple times a week. What was the time telling us before with the TX, TM stuff? So we'll look this up. This is like minutes per day, right? So every time you do math, for how long are you doing that? So we have 2 items, and of course you can like look at the documentation for like Eccles K, which can like take a lot of time because those documentations are like super long and it's like finding a needle in a haystack. This is why people say like learn to use a data set, publish a lot out of it. Don't try to learn too many data sets. I think I've like touched like 9 and dying. So because you know like how often something has happened, right, in terms of like days per week, right? And then you know every time it happens, how many minutes for which someone has spent the time, you can kind of compute, right, with some assumptions, how many minutes per week somebody spent on math or reading. Okay. Now, this is the variable list. And I'll summarize this so you can look at it. Right. We're looking at for math and reading, right? For times 2, 4, and 5, how often they did it, and for how long they did it every single time. And we're gonna, clean the variable a little bit. We're gonna create a variable called min math for how many minutes per day you spent on math. And because these numbers are not numeric, right? Let's codebook this. Right? 1 tells me 1 to 30 minutes. 2 tells me 31 to 60 minutes. And oftentimes what analysts do is they like choose a number, and often like a median. All right, every time it says 1, right? We're gonna say that's about 15 minutes. Maybe you disagree with the assumption. Maybe you're like, kids are just lying or parents are just lying. It's really 1 minute. We should take the minimum. And that's, I don't know. It's up to you how you decide, like whether you take the minimum, the maximum, the median, or some value in between. For this exercise, we'll take the median value. So between 31 and 60 is 45. 61 and 30 is 75. And then for more than 90, we'll just cap it off at 100. Right? These are all decisions that you may have to defend. These are decisions that you might look for in the literature. You might say, maybe we should be like extra sure and say, let's use the min value for every single one of these, the max value for every single one of these. Are my analytic results sensitive to how I make a decision on these things? Or is it pretty robust? Because if it's robust, meaning it doesn't seem to matter what these decisions are, then oh, it doesn't matter how I do that. They generally give me the same thing. I have pretty good confidence on my answer. So this is the decision here. Same thing for often math, right? Never do it in a week, less than once a week, once or twice a week, 3 or 4 times a week, every day. Maybe some of these kids are, doing it on the weekends too, but we're assuming like, I think it might be like how often in the weekday. I'd have to look at the exact question, and you would have to too. But we're gonna say, well, if they told us 1, never, we're gonna just put 0. They just never did it. Tell us 2, less than once a week, we're gonna say 0.5. It's between 0 and 1. Same thing, a day and a half, 3.5 days, or 5 days that correspond to these categorical values. So now we have a variable that tells us how many minutes per day do they spend on math? How many days per week did they spend on math? We'll repeat for reading, but they also have it for week 5 or like time 5. So we'll just clean that too along the way. But the decision is the same. Take the median min value from these categories. Take the median day value from these categories. Okay. Questions on this? You will have to know them for the problem set, right? This is sort of what you're analyzing. Anyone feeling uncomfortable about what's happening here? Okay. If you feel uncomfortable later, let me know. So now we can take the product of those two things, right? Minutes per day and days per week to get minutes per week. So I create a time variable called time math2, which is going to be the time on math minutes per week in the spring of kindergarten. And then the same thing for time 4, which just happens to be the spring of 1st grade. I repeat for the reading. And then let's just combine them, like, because the total is going to give us how much time they spent on reading or math, right? And to make it easier to interpret so that you're not looking for a change in 1 minute, right? You don't care about a 1 minute difference in academic time, right? We'll standardize them so that they're in units of standard deviations. You have missing values because, not everybody is in the analysis. Okay. Now we're going to clean and create the outcomes.
Question.
Mm-hmm.
Can you I can't really tell why you standardize it in line
Here?
08 versus standardizing it earlier at 100.
At 100.
Oh, sorry, 400.
400.
Yeah, so like, can you standardize time read 4 first and then standardize time read math 4 first and then add it up?
I guess one might argue that, but if I want the amount of time that somebody spends on academic work, right? This gives me a better version of how long a student spends on reading and math, doesn't it? Like they spend, let's say, 100 minutes per week on reading and 200 minutes per week on math. How often, how much time did they spend on reading and math? The sum is a good way to cleanly get that number.
Yeah, I don't know. I guess I thought I was a little confused because I was just thinking like you can't compare the time that you spend on, for example, like reading versus the time that you spend on math. So maybe if you wanted to look at something like, I don't know, like teachers' expectation, well then if you had different expectations to begin with, then your scores would need to be standardized.
I guess so. So like this is one of the things that happen when your analytic decisions, when you look for creating composite scores, people will have disagreements on how you create them, right? Like let's say it wasn't as clear as minutes, and you can argue that every minute for reading and every minute for math, they're not the same, right? And I guess that depends on the conceptual decision.
Okay.
Let's say you had a reading like a score for like a measure of childcare quality that had one emphasis, say on cognitive stuff, a measure of childcare quality on emotional stuff, right? Some social emotional support. Maybe then that would say you should standardize them separately and then take the average between the two and then standardize it again, right? And so these decisions on how you get to the composite will depend on sort of the literature and what you believe best creates that variable. I think here, though, an argument can be made that, I mean, like it's the same problem that we'll run into when we look at outcomes. So maybe we'll save it for there. But I think when you're thinking about just the amount of time spent on academic work, it's okay to sum it this way. But I could sort of see your point that maybe what you should be comparing is the time spent separately, standardized, then averaged across or something like that. But I have a harder time on interpreting that one. But it might be that your analytic results are the same whichever way you run it.
Okay. I appreciate you explaining it. Thank you.
Yeah. But I mean, someone could entirely say what you said is defensible, but for now we'll just use this. Okay. It's the same thing happens here as an academic score. This is something that Greg does in his analysis too, where he just creates a composite. We have reading score, math score. Let's just take the average. Right? Maybe I shouldn't. Maybe they don't belong together. Maybe creating a composite is problematic. In which case you might run an analysis separately for reading and math. But to create a summary variable of our academic achievement, we're just going to take the mean. And then we're going to have to standardize this again, because once I've taken the mean of two variables, it doesn't give me a mean of 0 with a standard deviation of 1. Sorry, I meant to say mean of 0 and standard deviation of 1. So now what this does is it averages across academic scores at each time points, and then it re-standardizes them so that we have sort of a clean, standardized academic score that's a composite. And this here is just sort of a way for me to like just rename the variables. Okay. And we can check standard deviation of 1, a mean of 0. Okay. We've already defined our control variables, right? It's in our global. Now we just have to identify our sample, which is everybody, like we count the number of missing variables for all of the variables in our analysis like before. And then we only want the ones that are not missing any information. And here's one way to like get a sense for who's in our sample, which is not too different from our lab sample. But and that now, oh wait. Oh, all right, okay. That's sort of the relationship that you'll be looking at for the problem set. Time spent on academic work, academic achievement. What's their relationship? Okay, and that's it. I'll take questions on this data processing section, and then I'll take whatever questions you have. Any questions here? Anything from here that you feel uncomfortable with, unsure about?
So the data processing section is in the problem set, but you have done it for us?
It's in the lab9 file, and then all of this gets saved and processed here in a data set called 4PSA. And then when you go to open up your problem set, right? And I've provided the key.
Mm-hmm.
This is already done, so you don't have to do that again, right? It's just like loading up the data, setting the global for the controls so that you can use it later, right. And then running the models, right? The level model, simple change model, residualized change model, no controls, add fixed effects, add cluster standard errors, print them out. That's all this is.
Sure. Thank you.
Yeah. So there's like no need to code. I mean, there's something where I ask you like, like as a bonus, run an additional analysis, in which case you will code, but it shouldn't take you more than 1 or 2 lines. Or if you want to do something fancy, it'll take you more lines. Okay. Other questions on the data processing of what it went into the problem set? All right. If you have any, just let me know. And then any other questions on anything that's been covered in this lab?
Sorry, I know Miriam just asked. So even though number 2 on the problem set also gives hints, but the code is still there, right? So the hints are like a moot point.
No, the hints are about how to present the table, right?
Oh, they're about presenting. Okay.
Yeah, like I just want to make sure you don't forget stuff, because I just wrote a bunch of stuff. Well, I guess like
the first one you just showed us the controls.
Yeah. So like so I guess a part of it was about data processing, which I thought you would do a little bit of, but like you're not doing anything. But some of these are about presenting the table.
Okay.
The table shell is here.
Got it.
And you don't have to put in any of these numbers. I just want you to focus on these numbers.
Okay.
Yeah.
Thank you.
But like this entire table, right, with your notes will be worth half your grade on the problem set. I want to make sure you guys get used to like writing complete tables. That's what that's about. Okay.
So the last question that is about clustering standard errors. So there will be another hour of class that we have to watch for that.
I don't think so. So for this, I mean, like Greg is going to cover it in lecture. I don't know if he's going to do a recorded hour for you guys to see as an asynchronous part of the lecture, or if he would just cover it in the Monday class. But you don't have to understand what it's doing. I just want you to like look for what's changing, and you just be looking across to see what's changing, or what's not changing, I guess. But something is changing, right? but you have to know what's changing, what's not changing, right? I mean, I guess if nothing was changing, I wouldn't ask the question unless I was being a jerk and wanted to just catch people off guard or whatever. But I'm not, so tell me what's changing. Okay, other questions on the lab stuff?
One last question. So basically for the table, so like, if like, I'm not sure if it's cheating or not, but technically I can just use your table and type in the numbers.
Yeah. That's all you have to do because everything's provided. I mean, well, you have to run it, right? You have to run it to get the table. But
right, because I need the numbers. But like, I don't have to like go through that hassle of like, you know, getting rid of stuff on Excel or like adding lines and stuff. I can just type in the numbers in your table, right?
Yeah, that's right. You just have to move it over, but you have to present the information.
Gotcha. Thank you.
Yeah. Which is harder than you might think. Anyways, okay. So other questions on the lab file?
Could you go over the residualized change model again?
Sure. Let's start with your current understanding. Let's start here. We have run these models before, right?
Yeah, can you, I don't remember running them before. Was this early on? Can you just quickly remind me?
Yeah. So I think it's part of our replication of Frye and Levitt, where we're looking at achievement gaps, right? But then we control for like a pretest, where like we regress like a 5th grade math score on the race dummies, and then we control for like kindergarten entry test scores. So we've done this before, but and to see the entire table, you have to like zoom out. It's like here, right? This is the this is the lag test score. That coefficient is here. And so how would you interpret this model 9 and this parameter of interest, this predictor, our main predictor?
Can I actually go back a step and ask another question?
Sure, that's fine.
Yeah, I think what I am confused about is the purpose of a residualized change model. I don't think conceptually I fully understand it. And I think that's where I'm confused.
Yeah.
What makes it different from a simple change model?
Well, let's not
equationally.
Let's start here. This is the most basic equation, right? Right. This is looking at the relationship between self-control and 5th grade reading. You understand this, right?
I hope so.
I hope so too. I'm sure you do. So what happens if you control for this? Or like, let's say we control for these things. What are we saying?
That isn't it just the same interpretation, but you're just adding variables in to hold it constant. So yeah,
you're just
it's the same.
Right. You're just like with model 2, you're comparing students with the same race, ethnicity, gender, similar characteristics on child birth weight and other stuff. So when you look at model 9, what is this? You're just comparing students with the same kindergarten spring test score. Because it could be that maybe this is, let's say, like a proxy measure for ability. Higher ability students have more self-control and have a higher reading score as sort of your confound. So you control for that because maybe your pretest explains a lot, right? So model 1 and 9, the only thing that's different is you control for the pretest. And so this is the relationship between self-control and later reading outcome, controlling for, like comparing students who had similar kindergarten reading scores.
And this model 9 was a residualized change model?
Yeah, this was a residualized change model. A residualized change model is just controlling for pretest.
Okay, that's so much easier than I thought it was.
Yeah. And so you've done this before. You just control for pretest.
I literally can't call it a simple change model if I'm controlling for prior test scores.
A simple change model is not controlling for. Right? Your simple change models are here. I think it
But
was.
you can control for like every other demographic variable, but just not prior test scores, and you can call that a simple change model.
So if you control for this, I don't think it's a simple change model. A simple change is just simply changing the dependent variable.
So I think if you just subtract the lagged score from like a current score and then just predict that new variable, it would be like simple change.
Yeah.
But when you add it as a control, it would be residualized change.
Mm-hmm. Simple change, you just subtract the two. Okay. How are you feeling about residualized models, Tiffany?
I think I'm good. I think I just need to take some time to look over the code just to make sure like conceptual knowledge and like everything else kind of works. I think it's okay.
Yeah. So residualized models often make sense when you're trying to control for as many things as you can, right? To try and isolate this variance. But a change model sort of takes a different kind of approach, right? Like instead of putting this on the right-hand side of the equation, just kind of takes care of it on the left side of the equation. But you're not predicting the same thing, right? Over here, right, trying to compare kids who are similar in every way possible, including their prior ability that you want to try and measure. Right? You want to then look at the relationship between the self-control and later reading. And that's different from looking at how they change in their reading ability, right, as a function of self-control in kindergarten.
So kind of like in the real world, simple change model, that's the kind of hold on, that is different. Is that different from a cross-sectional model?
Yeah, a cross-sectional model means that you're using the same time points. So you would be comparing like self-control in kindergarten with reading ability in kindergarten. This is different in that the outcome is at a later time, not at the same time.
Okay, we're good. We are good.
Yeah, okay.
Thank you.
Other questions?
I have a question about the interpretation of the models. So I think I'm good on what simple change and residualized change models are doing, but when we look at the results like model 6 and 10, like if our dependent variable is the gain score and it's not significant, then can we say that the what was it again? The self-control isn't associated with how much score the child gains over time?
Yes. And just be specific about like when you measured self-control. It could be that self-control captured when they were like 3. I'm sorry, not 3, like in 3rd grade is related to later reading. But this is just looking at self-control captured in kindergarten.
But what I'm having difficulty understanding is like, but it's significant in model 10. So it actually is associated with a certain time point, like in 5th grade reading, even after controlling for kindergarten spring reading and all of the controls, but it's not significantly predicting the gain score.
Yeah, yeah, and that's sort of the like confusing part of like these like very complicated nuanced difference between residualized change and simple change, right? Because in a residualized change, you're not predicting gain, you're still predicting level, but you're just comparing kids who have the same score, same pretest score, or similar pretest scores. But maybe even if you compare kids with a similar pretest score, you cannot, and this is where I struggle too, right? It's like, I know it's not the same, right? Like, and you know mathematically that they're not the same, right? But teasing them apart is hard. But like here you are still like, even after you control for pretest, it doesn't allow you to sort of look at gains. It just allows you to see what happens to them later in life and whether this other like social emotional skill is predictive of that later academic skill at that level, which is different from, are they growing in that skill? But that feels weird because you would think, well, later they're kind of growing. I'm not very good at articulating the difference either. I don't run these models often, and they give me like pain. And so this is where I think like it's probably a good idea to ask Greg, who might be able to articulate it better. But my guess is Greg is going to start off by saying, residualized models are kind of awkward and hard to interpret, and they're not that useful anyways, and there are many better other models for you to focus on that give you a more transparent understanding of the relationship you care about. And it's my bet that that's how he's going to lead the conversation. And you're wanting to disentangle them and understand how precisely they're different beyond the mathematical difference is going to be hard. But I could be wrong. And you can start out by asking him, I know that there's a mathematical difference. I know it's not as good as these other ones. I still want to know, and maybe you'll get further in that conversation. But I'm probably not the best person to articulate that nuanced difference. Like there are situations in which a residualized, like controlling for the lag test score makes sense, and you do this all the time. Like if you run an experiment, you control for this. You try and run a quasi-experimental experiment, you control for this. You do it for different reasons. So controlling for pretest happens often. The residualized change has implications for a conceptual model that I'm not used to.
So I was thinking of an analogy. So maybe like as an athlete, to keep like the same shape, the same fitness, you have to like work out certain hours a week, for example. So the amount of hours you work is, for example, important for your fitness on your age 20 and will be important on your fitness on age 30. But that wouldn't necessarily result in any growth in your fitness because like you're working to keep like maintain the same fitness. And also like in like another way, so for example, your fitness at age 30 is also like reliant on your fitness at age 20 and how much you work out, but like doesn't necessarily result in growth in your fitness. I don't know.
Yeah.
I don't know if that makes sense or made it more clear or made you more confused.
Yeah. I mean, I know what you're saying, and it's one of those things where I can feel the difference, but I can't articulate it well enough, and I become skeptical that I have felt something that isn't there. I think, I guess if I was a better analyst, I should be able to more clearly tell you, right, beyond mathematical difference and coding differences, and that the results are different. But I'm not.
Yes. So in a sense, maybe you should, for example, keep your self-control to certain level, to just don't like don't like do the same as you did before in your math score. But so you are just trying to maintain your score. For example, you scored high previously and then you want to score high again. So you have to maintain some sort of self-control, but that self-control wouldn't necessarily result in your growth. It just is there to like keep maintaining the level that like you were on before.
Yeah, I think, and so Youngsun is probably gonna come back and ask the question. So sure, you did not find this growth here, but you see this change here. What does this mean? Why, when you have no growth, do you see the same change for the same unit of change in self-control? And I resonate with the question. I know it's not the same, but
So yeah, I think so. For example, having the same score at kindergarten, then if you just increase your self-control, then you can increase. But just increasing your self-control from kindergarten wouldn't necessarily result in your increase in the score, because like you will score higher in your kindergarten too. So it is like it will improve them to the same extent so that the growth would be still 0, but both would increase at the same time.
I think I'm following, but I'm not super sure.
Yeah, so probably if we just like do regression separately on both variables, we might like see like it has like very close coefficients. So it will like shows that both are dependent the same amount to it, like self-control. So like increasing your self-control would increase both of them like equally. So it wouldn't result in your growth, but it will increase them individually. But the fact that it is increasing them both, it just eliminates that growth.
Man, so we've reached that point where I can't help you, right? Like I'm pretty transparent with what I don't know. So my unverified wild guess at why these are different, which could be completely a waste of time for you, right? Is that maybe if when you compute a specific gain score, which is specific to the individual, you are and here we don't see that change in the gain. We're not seeing that change in the gain. And that's very different from thinking about a difference in the levels, which is not the changes in the growth. Meaning maybe there are other things that are like unmeasured that gives you a boost in the level, but doesn't give you a boost in the gains. So whatever unmeasured variable is giving you a higher self-control is also later giving you a higher level. But that same thing isn't operating to your gain score. But even this isn't super satisfactory, nor do I find it to be like exactly accurate. But I mean, so like we spent like 15 minutes now like hypothesizing about this difference, right? And you can probably tell, like if we spend 15 more minutes, we'll be circling the same level of confusion. This is where you have to find someone who actually knows the difference and not talk to someone who keeps telling you I don't exactly know the difference conceptually. Where I think maybe the 15 minutes was sort of an exercise in showing my futility in my ability to help you here. And maybe I'll bug Greg too, and he can provide more insight. You're not asked to understand this difference for the problem set. I can't even do it, so I won't ask anyone to. You're just asked to interpret one of these coefficients and the difference of adding in fixed effects. Okay, I have to run, but I know that you're not fully satisfied. I'm not either. Bug Greg. I know he's busy. I will also bug him. And maybe we'll have a better understanding of this difference, but or maybe not. It could also be that your advisors have a better understanding of this too. And they might have sort of a connection between a conceptual model to an empirical model that uses a residualized change as opposed to a simple change. But as Greg will point out, there are many different versions of change models that are better than both of these. So why bother with the ones that are giving you mental pain and agony? But I cannot speak for him. So, all right. So I'm gonna stop the recording here for now, at least.